Everyone, welcome to the deep learning workshop. In this video, I will provide a tutorial on introduction to transformer. Uh, Basically, we will see some sample code for each of the crucial component in transformer uh, block, namely position embeddings, multi-head self-attention, and so on. So this is the high-level overview of the transformer architecture. We have multi-head self-attention, which are the red blocks, and we have position by feed-forward, which are the blue blocks, and the layer normalization layers, which are the green blocks, and then the residual connection, which are the black arrows, right? Yeah, so there are two kinds of residual connection. One is for the self-attention layer, other is for the feed-forward network layer. So let's briefly look at the theory as well. So the code would be much more easier to understand. So the input that goes to a transformer model is as a tensor of shape batch size times number of tokens in a sentence, right? So if it's a batch, it's a max sentence length. This is what typically goes even to RNN or LSTM, right? Depending on um, depending on how it is processed, right? RNN process like one token at a time, while transformer process the entire batch at once, entire sequence at once, right? At least in the encoder side. And this first, it's the input embedding, the pink block. And the pink block is the NN.embedding layer, where it takes two inputs. One is the vocab size, number of unique tokens. And if it's encoder, we have number of unique encoder tokens. If it's decoder, we have number of unique decoder tokens, right? And followed by the hidden size. So when we pass the input to the NN.embedding, we would get a hidden embedding for each token in the current batch. So now the tensor would become from 2D to 3D. Now it's batch size times sequence length times the hidden size, right? So this is the new tensor which contains a token embedding. And remember that we transformer, we need to feed in the position information explicitly. So the position embedding is also additively added, right? So that addition operation is given here. The input embedding, token embeddings are additively added with the position embeddings. And we'll see later how the position embeddings are computed. And that's the core of it, right? Yeah. So let's start with the position embeddings. At least there are two popular ways to compute position embeddings. One simple way is to initialize them randomly um, and then learn them along with the task. So this is empirically better approach. Yeah, and the other approach, and the approach which was there in the original paper, is to initialize them based on sinusoidal embeddings. So it takes into account the dimension in the positional embedding as well as the position of the token. So it's a function where the even embeddings or the even dimensions are sinusoidal and the odd dimensions are cosine based, right? So we come up with a positional embedding of this form, and you can always wonder why we need to use this instead of the learnable ones. I mean, one advantage with using, some kind of a static embedding. So these are not really updated, right? These are static embeddings based on these formulas. Is that they are not biased towards the amount of examples across different positions, right? So sometimes some positions might have lesser data. I mean, probably there are not many examples in the training data set with a length at least equivalent to that portion. So those portion embeddings would get undertrained, so it would contribute negatively. So to avoid all of that, we can just go with static embedding, sinusoidal and cosine, and depending on the application, we can get results, right? Yeah, and depending on the application, we can decide the trade-off. Yeah, right. So let's try to see some code to create the positional embeddings, and it's very simple. So as you can see, the positional embeddings usually is the max sequence length times the intent size, and we can just run some two for loops. One for loop runs over the position, so it's the first dimension, and the second for loop runs over the embedding dimension, right? At least half of it. And the even dimensions are using sinusoidal, and then the odd dimensions are using the cost function. Yeah, right. And you can immediately compute, and you can inspect some of positional encoding. Say, well, the third portion, you can just index 2 and the colon, and it's going to give you the positional embedding for the third token. Yeah. And then you can even sum up. So what we eventually do is sum up the token embedding with the positional embedding, right? So we can do that. And this is finally the class for the positional embedding. So you can actually pass some input, and then you can add that input X. This is probably coming from the NN.embedding layer. You can add that with the positional encodings which you have just created. Yeah, and that's precisely what goes to the transformer encoder block, right? And you can plot it, and you can see nicely, some of them are sinusoidal, the even ones, and the odd ones are cosine based, right? You can just see. Yeah. And that's pretty much, yeah. And in, at this point, I mean, I've said the positional embeddings can just be randomly initialized, and they can be learned from scratch. So if we want to do that, we can do that using the NN.embedding layer themselves, and then the number of embeddings is equal to the maximum sequence length, and then for each such token or each such portion, we need a item size, right? So we can give that, and then we can check all that, knowing what portion embedding for based on the portion. Yeah, so we can do that. And yeah, and once that is done, right, so we have added, and we can pass it to the multi-layered self-attention, right? So now we'll see how that is done. And remember that whatever be the block, we would add a layer normalization from the output of it, and then add it. This is the skip connection. The residual connection, right? Add it with X. And this is going to be the output of the first sublayer at least, right? And this is technically the idea which is also used from the feed-forward output. Yeah. So instead of FSX, FFX could be a sublayer, it could be self-attention, or it could be position-wise feed-forward, and that is the job. Yeah. So that's pretty straightforward. So even like PyTorch has an NN.layer norm module which you can readily use. That's not really an issue. So what is the biggest issue is how multi-edge self-attention works. So let's try to understand how it works from assuming that we have only one edge, right? So we know that the input is projected into query, key, and value. And the query is used to find the learn the alignment score between all the other tokens in the input. So it is multiplied for a given token with all the key values from all the other tokens, including the token itself, and then compute the alignment score. And then the alignment score is scaled down by the square root of 1 by the square root of the embedding size, the query embedding size. uh, and then it is going to the softmax. So we are converting that alignment score into probability distribution, and we are using this probability distribution to compute a weighted average of the or weighted sum of the value embeddings, right? And that's the final result that we have. This is the computation which goes to self-attention logic for one single attention net. And so we have some matrices. WIQ is the projection for query, WIK is the projection for key, and similarly WIV is projection for value embeddings. And we get these outputs. And once we get these outputs, we can actually see how we can do similar computation if we have multiple attention nets. So it's fairly straightforward, where we actually take the projections and we divide it by the number of attention nets, and then divide that space into multiple subspaces, and then the attention mechanism happens in each of these subspaces, right? And then finally we get the output, we concatenate from all the subspaces, and then we put an output layer to concatenate to capture the interactions between these different subspaces, right? And once that's done, and what we have is an output. So first let's start by looking at some sample code for computing attention for a single edge case. So we have query, key and value. So we start by doing the matrix multiplication of query with k, and we get the raw scores. These are the alignment scores, and we typically want to check if we have any mask, or this happens when we are actually doing this self-attention score computation in the decoder side, right? When we don't want the self-attention logic to process tokens in the future. We are only going to work with the current tokens and the tokens in the past, right, to maintain that auto-regressive context. So if we see that mask is there, then that means that we are doing self-attention for the decoder side mostly, and decoder side, and that's the self-attention decoder logic, and we ensure that the masked tokens are not seen, right? Their scores are set to negative infinity. And once that is set, then softmax is done to compute a probability distribution. So those tokens which are masked out will never get picked up, and we use the probability scores to finally compute the updated hidden representation. So you just do matrix multiplication of the probabilities with the value embeddings. That is all. And you get attention score, right, for a single attention net case. And to generalize, we can implement the same idea on different subspaces. So what we do essentially is we have query key and value. We project them with the first to query key and value embeddings. So we get that linear projections, and once that is done, we can pass to the attention function to compute self-attention in each of the representation space, and then we actually apply the output, and so we already get the value embeddings, right, from the attention logic. And once we get the value embeddings from each of the subspace, then we actually try to concatenate them, and then we pass it to our output layer, right, to capture the interaction between different subspaces. So that's essentially what we do, and that's multi-edge self-attention. At its core, it's very simple, but it works really well. Yeah, and followed by the output, the only thing which is missing from this entire transformer block is the feed-forward net. And feed-forward net is quite simple. It's just nn dot linear. So we have the xa, which is the input. We first do nn dot linear, so that's what happens here. And then the output is going to the ReLU layer, and then that output is multiplied with another nn dot linear layer, and that would be the result of feed-forward net, right? And putting everything together, and this is essentially one transformer encoder block, right? And it's easier to see how we can adapt that for the transformer decoder block, where we also have in between a cross self-attention, right? Yeah. So this is the gist of transformer block. So far we have seen sample code for question embeddings, a multi-head self-attention, and in the next video we will look at running transformer for the machine translation task, where we would readily use nn dot transformer module. Yeah. I think that is mostly it, and if there are any clarifications or any questions, feel free to contact us. Thanks a lot.